Alright, 6.3, Riemann sums and definite integrals. Uh, so what I'm hoping with this definition, and it's going to wrap up on the next slide, is that we're slowly going to, through this section, connect what we did in the last section to the idea of a definite integral. So here's the definition. Let the function f be defined on the closed interval a to b, and let delta, that's just a triangle looking thing, delta, or means change if you remember certain ways we write the slope formula. So delta be the change, be a partition of interval a to b, given by a equal to series of x sub 0 less than x sub 1 all the way to x sub n equal to b. So a being the smallest and b being last, where the change in x sub I is the width of the subinterval. If c sub I, this right here is c sub I, b, if c sub I is, I wrote that terribly, is any point in the ith subinterval, being x sub I minus 1 comma x sub I, then the sum. Now let me give you some context, because that looks like a bunch of gibberish to you probably. So if do you remember making those rectangles whenever we were trying to find the area of those rectangles from the left side to the right side? So when we're saying the width, our goal here with finding a definite integral, which we're going to eventually do, is we're going to find the area under a curve. Okay, so with x sub I being the width, that little width, that the width of each of those triangles at the bottom. That's what it's referring to. Okay, so a little context there. So now we're going to finish up this definition on the next slide and define this sum, and a little bit of the the sigma notation like we did in the previous lesson. Summation of I equal to 1 to n of f of c sub I, the change in x sub I, for some c sub I in between x sub I minus 1 and x sub I. Okay, so what we are doing is, remember how we had all those, well, I know I said this in the last slide, but we had all those rectangles that we drew to try to approximate what the area under the curve is. By this c sub I is going to approximate it so that it is perfectly the area under the curve. Okay, so it's no longer going to be the length of 1; it's going to be pinpoint to a specific point. Okay, that's called the Riemann sums for partition delta, or a change. So our goal here with this lesson is we are no longer going to be doing the rectangles except for your quiz, and we're going to be able to approximate exactly what that area is. That's the goal. So now we go to the definite integral. So the limit is going to be approaching 0. Okay, meaning, because if it was, we were kind of finding all those bases of 1 and 0.5 and all that before to kind of pinpoint what exactly the area is. But if we get it to 0, we're going to get a bunch of areas that are perfect under the area of the curve instead of doing a big rectangle, as it's getting closer and closer to 0. If this exists, this limit right here exists for a closed interval a to b, right? So we still have that same closed interval a to b, and the limit of Riemann sums over this partition, if it exists, then we can say that the function f is integrable on the interval a to b, and the limit is noted by limit. What this is called partition right here, partition, laser work, partition as it approaches 0 of the summation of I equal to 1 to n of f of c sub I with the change of x sub I. That equals our definite integral. Alright, so what we are doing is, as we get closer and closer to get an exact area under a curve between a and b, we get our integral. We're going to do one example where we use some of the stuff we did in the last section for the Riemann sums, and then we are going to be using after that just simply integrating like we did in the first section of this chapter, and then evaluating from there. Alright, so here's our first definite integral we're going to find using Riemann sums. Or rather, I guess I should say, using the limit. So we have this definite integral right here. Some things we need to find based off our definition. We need to find change in x, right? Which is simply just the upper limit minus the lower limit. Okay, this is what we call when we're working with definite integral, lower limit, upper limit. So we do this minus this, which is 5 over n. We're going to need that in order to solve. The other thing we're going to need is c sub I, which is always going to be a plus I times change in x. So it's going to be negative 2, which is a, that's a right there, plus what that is, okay? I. So 5i over n plus negative 2. So we need that in order to start. So I'm going to write my limit next. So what I did here is I wrote my limit as n approaches infinity of the summation of f of ci times delta x. So I plugged in f of ci. I plugged in this everywhere there's an x. Okay, there's one x right there. Okay, and then our dx, or our change in x, which is what will be part of our quote-unquote integral later, would be just simply this, right? So let's start simplifying it. So I'm going to move that 5 over n up front. And I just realized I forgot the summation right here. Okay, that 5 over n goes in front of that summation next. So 5 over n, same limit. Okay, and summation of I equal to 1 to n of negative 2 plus 5 I over n. So what do we remember about the whole I portion of what we did before? Well, hopefully remember that it's equal to n times quantity n plus 1 over 2. So I'm going to have the limit as n goes to infinity of 5 over n, parenthesis, negative 2 plus 5 over n, parenthesis, n times quantity n plus 1 over 2. We simplify this, and you're going to get, regardless, you get n right here, right there, negative 2n. So that does simplify to keep that, keep the parenthesis, keep the negative 2n for now. And then we'll get that numerator, so we'll simplify it, so that numerator is going to go to 5n squared plus 5 over 2n. Forgot the n. Yeah. Now all I did was distribute the n to the n plus 1 and multiply by 5. Simplify more. And that will get us plus 5 over 2 and up top plus 5 over 2. Distribute to 5 over n. You're going to get negative 10, still limit, I'm doing the 5 over n, so negative 2 times 5 is negative 10. N over n goes away, so it'll be negative 10. N's cancel again, because it ends on the numerator. So I'm going to get plus 25 over n, not over n, over 2. And we're going to get, 25 plus 25 over 2n. So we evaluate the limit. This portion right here goes to 0. And then this add up. And you're going to get 5 over 2 as an answer. Because all you have to do is just add up these two values, and you'll get your solution. So we're going to talk about different properties of definite integrals now. And there's two special definite integrals that we're defining right now. And that is this first one. If f is defined at x equal to a, then we define the integral from a to a of f of x dx to be equal to 0. Meaning, if your upper and lower portion of the integral are both the same, it's equal to 0, no matter what the function is. Okay? And then second special integral is that anytime we have an upper or lower limit of b to a, we can swap it and make it a to b and put a negative sign in front. Okay? As long as you put the negative sign up front, you can flip the upper and lower portion of the integral. We'll do one quick example. So let's say if we are integrating, I'll go on right here, integrating 3 from, let's say, from 2 to negative 1. What we can do before dx, we need a dx there, can't forget that. We can put a negative sign up front and make it from negative 1 to 2, and then we can evaluate it. So evaluate the integral will just be equal to negative 1 to 2 of 3x. So we're going to get 3 times 2 minus 3 times negative 1, which will get us 9. So negative 9, because we can't forget the negative up front. All right, so some properties of definite integrals. If f and g are integrable on a comma b, and k is a constant, then the function kf and f plus or minus g are integrable on from a to b. And here are the rules written out. Anytime we have a coefficient or some constant we're multiplying by, we can move it up front so it'd be easier to integrate. And then every time we're adding or subtracting, we can separate them and integrate each function individually. We'll do an example where we do that right now. All right, we've got the integral from 1 to 2 of x squared plus 1 dx. So using our property, we can separate this into two different integrals. Those are two different parts of the polynomial. And when we integrate it, we're going to get x to the third divided by 3 plus x. And remember, we're evaluating it from 1 to 2. We put 2 in. 2 to the 8 is 2 to the third power is 8 over 3. 8 over 3 plus 2 minus 1 cubed is 1. 1 over 3 plus 1. That's going to get us 14 over 3 minus 4 over 3, which is equal to 10 over 3. And that's your answer. I appreciate you watching, and we'll see you in class. Bye-bye now.